nanoHUB-U, online instruction.
Welcome back to the last lecture now of Unit 1 of our course. I guess it's time to sum up. Well, as you know, when we're talking about current flow or transport, it usually involves these two types of processes. And so in part A of this course, we are talking of semi-classical transport using semi-classical mechanics, the particle mechanics, and then there's the entropy-driven processes, and when you put that together, you have the Boltzmann equation. So for part A, our standard kind of starting point in thinking is usually this Boltzmann equation, and what we try to convey is that using this idea that in nano devices you can think by separating out the two types of processes, you can get a simplified view, simplified way of looking at things. And that viewpoint is what we are also continuing in this part into quantum transport. Of course, instead of Newton's laws, we now have the Schrdidider equation that describes the wave nature of electrons. And that's this E psi equals H psi. And H is what describes the energy levels in the channel. And here again, we have to start from Schrodinger, but then that's not enough. You have to add these entropy-driven processes to the story, and that's this non-equilibrium green function method, which is what we'll be going on to in the next unit. In this unit, what we have really talked about is just this, the mechanics part, the Schrodinger equation part. So what we showed was, you see, if you're interested in a solid, like this, again, the starting point would be the Schrodinger equation, which was first written down in the context of understanding the spectra of hydrogen atoms, but since then has been applied to in all atoms, molecules, solids, everywhere. The starting point is, again, the Schrodinger equation. Of course, in a hydrogen atom, the potential that appears is only the potential due to the nucleus, whereas in any solid, you have to include a component due to all the other electrons, which is what makes the calculations much more difficult and elaborate. Now, a method that is widely used in this context for solving the Schrodinger equation is this idea of basis functions, that you take this quantity, the wave function that you're looking for, and write it as a linear combination of some known functions. What do you use for the known functions? Well, people use all kinds of things. What we are using here, what we are generally talking about in this course is what you might call atomic wave functions. That is, if you looked at one of the atoms, what the wave functions would have looked like. Of course, in general, for every atom, it wouldn't be just one wave function. There would be a few of them. There could be a 2s, 2p, etc. There would be multiple wave functions at the same atom. And the thing is, you take all these basis functions, a few localized around each atom. And overall, if you have n basis functions, then you can turn this Schrodinger equation into a matrix equation, where that matrix is n by n. And in the first principles method, of course, you would calculate the elements of this matrix from first principles. And there's a definite prescription on how to do that. In the semi-empirical method, which is what we are doing, the idea is to write it in terms of a few parameters and then obtain those parameters by comparing with a few standard experiments. And once you have this, then you can go on to describe all kinds of other experiments. And there, what we spent most of the time in this unit talking about is how you can write down the eigenvalues of a huge matrix. This is a huge matrix because, after all, these basis functions, you have a few basis functions per atom, per unit cell. And let's say you have thousands of these, then this is a huge matrix. But the basic lesson that I was trying to convey in this unit, what we spent a lot of time talking about, is that because it's periodic, you can actually write down all the eigenvalues without going to a computer. You don't have to solve this entire huge matrix, thousands, 1000 by 1000. You can just write it in terms of a small matrix. And what determines the size of the matrix? Well, it's the number of basis functions per unit cell. So we took the case of graphene where you could do it with 2 basis functions per unit cell. In general, you might need much more. Graphene is a particularly nice example because it's very relevant to research, and the nice thing is that this 2 by 2 description actually gives you fairly good results, based on which people actually write professional papers. Okay? On the other hand, in many other cases, to get good, reliable results, you would need to use many more basis functions per atom. So let me say a few words about what you'd need to handle silicon, for example. You see, silicon is something we didn't at all address in this course, in this unit so far. You see, and we won't be talking about this very much either. But let me just take a slide to give you a flavor of what it would be involved if we wanted to do silicon, a very common semiconductor. Well, silicon, as you know, has an atomic number of 14. So if you looked at the atomic levels, there would be the 1s level, which would accommodate 2 electrons, again because of the 2 spins as we have mentioned. There will be 2s and 2p, that's 4 levels, which accommodate 8 electrons, so that's the 8. So 8 and 2, 10, and that leaves another 4 electrons for the n equals 3. And when you go to the n equals 3, you have again the s states and the p states. So if you look at that, 4, which could accommodate 8, but then there's only 4 of them. And then there are higher levels. There's the 3d, there's 5 of them there. And then there's 4s above it, and so on. That's all. So when you are trying to write down the basis functions of a unit in a unit cell, what you'd use is the basis functions for one atom, and then you ask, well, how many atoms in a unit cell? Well, these common semiconductors all have what's called a diamond lattice. And a diamond lattice is like an FCC lattice. FCC is face-centered cubic. What that means is you have squares like this with atoms at the corners of the squares and one atom at the center of each face. So if you turn around, every face has one atom at the center. So that's what you call a face-centered cubic lattice. You could easily Google that and look up the pictures on the web if you cannot see this very well. But all this diamond lattice then, the way it is different from the FCC is that here I'm showing just one atom at this point, but in all these common semiconductors like silicon, you'd have 2 silicon atoms at each point. So it will be one here and another one a little bit off on this side. So the unit cell is actually 2 silicon atoms. Just as in graphene, the unit cell was 2 carbon atoms. So here you'd have 2 silicon atoms. Okay. So with these 2 silicon atoms then, you'd have something like this. And again, to get a good description then, how many basis functions would we use per unit cell? Well, usually as we discussed, you don't use the core electron, these core states at all. So leave that out. So you get 1 and 3, 4 here, 1 and 3, 4. So you could use 8 of them. And usually people also include the spin explicitly into the description. So it's 16. So a lot of the band structure of silicon, the minimal amount people would use is 16 basis functions per unit cell. What that means is when you plot it out, it will look like a complicated diagram. There will be 16 branches to it. Remember, in graphene we had 2, and so we had 2 branches. Now there will be 16, some overlapping. So often, people call it the spaghetti diagrams. You see all these lines going every way, right? And it takes, it takes some time to get yourself oriented and see which bands are coming from where. And all that we didn't talk about in this unit at all. I'm just trying to give you a flavor of what the band structure looks like for real solids, other than graphene. So the minimal amount is 16 basis functions, but then people use more basis functions to get better descriptions. Sometimes people use the 3D levels. Sometimes people use the 4S levels, or both. And that would again give you many more basis functions, and so many more lines to the band structure. And the other question that we could ask is, what's the Brillouin zone look like? What's the reciprocal lattice? Well, again, the basic unit cell, of course, has this face-centered cubic structure, as I mentioned. And you can show that the reciprocal lattice of a face-centered cubic structure is the body-centered cubic structure. Body-centered means you have this square, the cube as before, but the additional atom is in the center of the cube and not on the center of the face. And then that's the reciprocal lattice. And so if you want the Brillouin zone, so I'm bringing it here so you can see it, that's the Brillouin zone. So you kind of look at those reciprocal lattice vector and draw bisectors. And when you draw all those bisectors, you'd get this complicated geometric shape here, and that's the Brillouin zone. So all these details, of course, take time to get used to, and we'll not be talking about it in this course. You see. What we did in this course instead is we talked about the basic principles starting from simple 1D solids and worked up to I guess the highest level of complexity we reached was this graphene. And in graphene, again, as I said, it's instead of 2 silicon atoms per unit cell, we now have 2 carbon atoms per unit cell. And carbon has a lower atomic number. It's like 6. And so it's only the n equals 1 and the n equals 2 levels. And then, of course, the n equals 1, these being the core levels, you usually don't include. So you have the n equals 2 levels. But here you might say, well, that's the situation is just like silicon, because after all, you got this 4 here and 4 here, so you'll need 8 basis functions per unit cell. And that is kind of true if you want to describe all these levels, but the enormous simplification in graphene that you have is that when it comes to current flow, again, the ones that matter are these levels, because those are the closest to the Fermi energy, which is in the middle, and those can be described largely in terms of the pz orbitals. What that means is you could just use 1 basis function per atom, which means 2 basis functions per unit cell, and still get a reasonably good description of the energy levels of graphene. And that is kind of what we built up to in this course, and we talked about how you can analyze it. Now, one thing I should mention that you can get these energy levels of a uniform sheet of graphene, assuming periodic boundary conditions, just from this 2x2 matrix. Of course, when we do current flow in small structures, then you cannot use the band structure anymore, because it's not an infinite sheet with periodic boundary conditions. Then, of course, you have to do the real structure. And if the real structure has 100 atoms, you'd have a matrix with 100 basis functions. So it will be a 100 by 100 matrix, no question, right? Right now, all we are trying to do is figure out what are the right parameters to use for this T, for example, the one that connects 2 neighboring carbon atoms. So what we want to know is the eigenvalues of this infinite sheet of graphene and compare it to experiment, and based on that, extract a suitable value of T, so that later on, when we talk about current flow in graphene, we can use that T. And what we showed, I guess, in these lectures is that because you can use just 2 basis functions per unit cell, you can extract these eigenvalues just from a 2x2 matrix. And this 2x2 matrix, the eigenvalues are given by this epsilon plus minus the magnitude of H0. And there again, you can simplify this expression somewhat, which is commonly done by looking at the valleys. That means the points where this H0 is a minimum, because that's where the energy levels will be closest to the Fermi energy. And these valleys, when you look at in K space, you see them kind of spread in this hexagonal pattern here. See? And offhand, you might think there are 6 valleys, but the point we try to make is that actually it's only 2 valleys. And for that, you have to consider this Brillouin zone. And around each one of those valleys, you can make this approximation so that E just looks like it's proportional to K. And that is, of course, one of the very important properties of graphene that distinguishes it from the common semiconductors. Common semiconductors, E is proportional to K squared. h bar square k square over 2m. Here, around those values, you can write it as E is this AT times K, because this is the magnitude of K. Okay? And if you construct this reciprocal lattice, what you see is those 6 values are actually 6 1/3 values, and so you have these 2 effective values. And that, as I have mentioned before, has a very direct experimental consequence, namely, the ballistic conductance usually is 25 divided by 2 kilo ohms, like 12.5 kilo ohms, because of the 2 spins. In graphene and in carbon nanotubes, it's more like 6 kilo ohms, because there's also the 2 valleys, because all these valleys and spins are like, conceptually like conductors all in parallel, which reduces the resistance by that much. And also because E is proportional to K, we have this simple relation here. You could extract the velocity. What is the velocity of an electron in graphene? Well, there is this, that usually velocity is proportional to K, but here, because E is proportional to K squared, and velocity being derivative of E with respect to K is usually proportional to K. Here, E is proportional to K, and so the velocity is a constant number. Doesn't matter what the K of electrons is. And this comes as a surprise because, as you know, ordinarily we think that velocity is like h bar k. I mean, rather, momentum is like h bar k. And so, more the k, more the momentum. And if there's more momentum, you'd think there's more velocity. Well, not really, as far as, not in general. In this context, yes, momentum is h bar k, but the velocity is independent of that. It's a constant number. How much is that? Well, you can put in the values. A, that's very well known because that's basically this distance. As you know, this is the arrangement of atoms in graphene. So you have a carbon atom here and a carbon atom here. That bond length is known to be, I guess, about 1.4 angstroms, 0.14 nanometers. And so A is like 1.5 times that. So that's the 0.2 nanometers. And that leaves only one other parameter, T. I mean, h bar, that's Planck's constant. I mean, that's well known. That's a universal constant. So when you put that in, if you put T equals 3 eV, you'll get about 10 to the 6th meters per second. And in graphene, what's experimentally known is that velocity is about 8 times 10 to the 5th meters per second, I think. I mean, in this order, and depending on what velocity you choose, you can adjust your T. So that kind of illustrates this principle of the semi-empirical method, because the idea is we are turning Schrdidider equation into a matrix equation. And that matrix has only one parameter, this microscopic parameter, the T. How do I choose it? Well, I choose it by making sure that I match certain standard experimental results. So in this case, I could say I use the appropriate T so that I get the right velocity. Right? And it just depends on that. So with that introduction then, this unit was intended to introduce to you the Schrdidinger equation, but more importantly the matrix version of it and how you get the parameters of that matrix. And now we are ready to move on to talking about current flow or transport problems. And as I mentioned before, transport problems, it's not enough just to have quantum mechanics. You kind of need to have these entropy-driven processes. In other words, to start with, even if there is no interactions in the channel, you still have these contacts where all these entropy-driven processes work. And so what we need is to figure out how to take this Schrdidinger equation, which describes an isolated channel, and attach contacts to it. And so that's why we call it contacting Schrdidinger, and that's what we'll be talking about for the next 2 units of this course. Thank you.